Welcome to a journey through the periodic table, the universal catalog of matter. In this guide, we'll unlock the hidden patterns, predictive power, and electric forces that shape the elements. The periodic table isn't just a chart, it's the decoder ring for the universe, revealing how everything around us is built from a handful of fundamental building blocks. From the air we breathe to the technology in our hands, every material traces back to these elements. Let's begin by understanding how this table is more than a list, it's a map to the structure of reality. Periodic table is more than a scientific tool, it's a visual map of all known elements. Each box represents a unique type of atom, and together they form the foundation of everything in the universe. The table structure is carefully designed to reveal relationships and trends among the elements. As we explore its layout, you'll see how it organizes the building blocks of matter in a way that's both logical and predictive, making it one of science's greatest achievements. To truly understand the periodic table, you need to know how to read an element's box. The atomic number is key. It tells you how many protons are in the nucleus, and this number defines the element. Change the atomic number and you change the element entirely. The symbol is a universal code, often derived from English or Latin names like Hg for mercury. This shorthand allows scientists worldwide to communicate clearly about the elements, no matter their language. Next, let's look at atomic mass. This number isn't always a whole number because it's a weighted average of all the natural isotopes of an element. Isotopes are atoms of the same element with different numbers of neutrons. While the number of protons defines the element, the number of neutrons can vary, giving rise to isotopes with slightly different masses. This subtle difference is crucial in fields like chemistry, physics, and even medicine. Periodic table is organized by increasing atomic number, but there's more to its structure. The horizontal rows are called periods. Each period corresponds to the number of electron shells an atom has. As you move down the table, atoms gain more electron layers and become physically larger. This organization helps us predict how elements will behave and interact with others, making the table a powerful tool for scientists. Vertical columns on the periodic table are called groups, numbered from 1 to 18. Elements in the same group share the same number of valence electrons, the electrons in their outermost shell. This similarity gives them nearly identical chemical properties. For example, elements in group 1 are all highly reactive metals, while those in group 18 are stable noble gases. Understanding groups is key to predicting how elements will react. Valence electrons are the outermost electrons of an atom, and they determine how an element will interact with others. Elements in the same group have the same number of valence electrons, which is why they behave so similarly. For example, all group 1 elements have one valence electron, making them eager to lose it and form bonds. This simple rule explains much of the periodic table's predictive power. Let's look at group 11, sometimes called the currency group. It contains copper, silver, and gold metals historically used for coins. These elements are malleable, highly conductive, and relatively non-reactive. Their shared properties come from their similar electron arrangements. This is a perfect example of how the periodic table's organization reveals patterns in the natural world. Why is it called the periodic table? Because when you list elements by atomic number, their properties repeat in a predictable rhythm. For example, you'll see a pattern of reactive gases, stable gases, and reactive metals. The table wraps this timeline around so that elements with similar behaviors stack vertically. This periodicity is what makes the table such a powerful tool for predicting chemical reactions. Ultimate goal for most elements is to achieve the stability of the noble gases, found in group 18. These elements have a full outer shell of electrons, making them extremely stable and unreactive. All other elements strive to reach this configuration, either by gaining, losing, or sharing electrons. This drive toward noble gas stability is the engine behind all chemical reactions. How do elements react? It's all about achieving a full outer shell of electrons, just like the noble gases. This arrangement is the most stable, and elements will do whatever it takes, lose, gain, or share electrons to get there. This quest explains why sodium reacts explosively with water and why chlorine is so eager to bond. The periodic table's structure makes these patterns clear. Group 18 is home to the noble gases helium, neon, argon, and others. These elements are famously unreactive because they already have a perfect arrangement of electrons. Their stability is so complete that they rarely form compounds. The rest of the periodic table is essentially a story of elements trying to achieve what the noble gases already have. Powers all of chemistry. It's the drive of elements to reach noble gas stability. This quest for a full outer shell explains why elements bond, react, and form the vast array of substances we see in the universe. The periodic table's organization makes it easy to see which elements are close to stability and which are far away, predicting their behavior at a glance. The periodic table is divided into metals and nonmetals with a clear boundary between them. Metals are typically shiny, conductive, and malleable, while nonmetals are more likely to be gases or brittle solids. This division helps us understand why elements behave so differently and why certain materials have the properties they do. Between metals and nonmetals lies a staircase-shaped region occupied by the metalloids. These elements have properties of both metals and nonmetals, making them unique. Metalloids are essential in technology, especially in electronics, because they can conduct electricity under certain conditions, acting as semiconductors. Metalloids are the hybrids of the periodic table, blending properties of metals and nonmetals. They can conduct electricity like metals but also act as insulators like nonmetals. This unique combination makes them crucial in the development of electronic devices and modern technology. Silicon, a metalloid, is especially important because it acts as a semiconductor. It can switch between conducting and insulating electricity, which is the foundation of all modern transistors and computer chips. This on-off capability has revolutionized technology, making computers and smartphones possible. On the far left of the periodic table, you'll find the alkali metals in Group 1. These are extremely reactive, soft metals that are desperate to lose one electron to achieve noble gas stability. Their eagerness to react makes them fascinating and sometimes dangerous to work with. Next to the alkali metals are the alkaline earth metals in Group 2. These elements are also reactive, but they need to lose two electrons to reach stability. Their chemistry is a bit less dramatic than the alkali metals, but they're still essential in everything from fireworks to bones. On the far right, just before the noble gases, are the halogens in Group 17. These elements are highly reactive and exist as gases, liquids, or solids. They are desperate to gain one electron to complete their outer shell, making them powerful agents in chemical reactions. In the center of the table, Groups 3 through 12, you'll find the transition metals. These classic metals like iron and copper have complex electron behaviors that give them unique properties. They're essential for construction, electronics, and even biological processes. At the bottom of the periodic table, you'll see two rows, the lanthanides and actinides. These elements actually fit inside the table but are placed below for design reasons. They include rare earth metals and radioactive elements, playing crucial roles in technology and energy. The periodic table is divided into metal and nonmetal territories. Metals dominate the left and center, while nonmetals cluster on the right. This division helps explain why metals are good conductors and nonmetals are often insulators or gases. The boundary between these territories is where you'll find the versatile metalloids. Hydrogen sits in Group 1, but it's not a metal, it's a gas. With only one electron, hydrogen can lose it like a metal or gain one like a nonmetal. This unique ability allows hydrogen to play both sides, making it one of the most versatile and important elements in the universe. Elements don't have personalities, they act according to the laws of physics. Chemistry is ruled by the electric force, which is millions of times stronger than gravity. This force drives the transfer and sharing of electrons, shaping the behavior of every element on the table. Nonmetals like chlorine have a massive electric pull, allowing them to rip loosely held electrons from metals like sodium. This transfer creates ions, which then bond together to form compounds like table salt. The electric force is the invisible hand guiding all chemical reactions. When electrons are transferred from one atom to another, ions are formed. These charged particles are the building blocks of countless compounds. For example, sodium loses an electron to become positively charged, while chlorine gains one to become negatively charged. Their opposite charges pull them together, creating a stable compound. The periodic table is more than a list, it's a map for predicting how elements will behave. By knowing an element's group, you know its number of valence electrons. This lets you predict how it will interact with other elements, forming the basis for all of chemistry and material science. An element's position on the periodic table tells you its destiny. Its group reveals its valence electrons, and those electrons determine how it will bond and react. This predictive power is what makes the periodic table such a vital tool for scientists and engineers. With just over 100 elements, the periodic table provides the foundation for the infinite complexity of the universe. Every material, from the simplest gas to the most advanced technology, is built from these basic building blocks. The table's organization helps us understand and harness this complexity. The periodic table's greatest strength is its ability to reveal patterns. By grouping elements with similar properties, it allows us to predict behaviors, discover new materials, and even design new elements. This pattern recognition is at the heart of scientific discovery. Each period on the table represents a new electron shell. As you move down the table, atoms gain more shells, making them larger and changing their chemical properties. This layering is crucial for understanding why elements behave the way they do. Elements in the same group are often called chemical families because they share traits. For example, the alkali metals are all soft and highly reactive, while the noble gases are all inert. These family resemblances make the periodic table a powerful tool for organizing knowledge. Electrons are the real actors in chemistry. Their arrangement in shells and their movement between atoms drive all chemical reactions. The periodic table's structure is built around these electron patterns, making it a roadmap for understanding the invisible world of atoms. When elements interact, they form molecules, combinations of atoms held together by chemical bonds. The periodic table helps us predict which elements will bond and what kinds of molecules they'll form. This knowledge is the foundation of chemistry, biology, and materials science. Every element is represented by a unique symbol, often derived from its English or Latin name. These symbols are the language of chemistry, allowing scientists to communicate complex ideas quickly and clearly. Mastering these symbols is the first step to understanding the periodic table. Atomic mass is a weighted average reflecting the abundance of each isotope in nature. This subtle detail is important for calculations in chemistry and physics, affecting everything from reaction rates to the behavior of materials. One of the periodic table's greatest strengths is its predictive power. By understanding an element's position, you can anticipate its properties, reactions, and even its role in new technologies. This foresight has driven countless discoveries and innovations. The periodic table's design isn't just for looks, it's functional. The placement of the lanthanides and actinides at the bottom keeps the table compact and readable. Every aspect of the layout serves to highlight relationships and trends among the elements. With just over 100 elements, the periodic table decodes the infinite complexity of reality. Every material, every living thing, and every technology is built from these simple building blocks. The table's organization helps us understand and manipulate the world at its most fundamental level. The periodic table isn't just for scientists, it affects our daily lives. From the metals in our electronics to the gases we breathe, the elements shape everything we experience. Understanding the table gives us insight into the materials and processes that power our world. The periodic table is a living document, constantly expanding as new elements are discovered and new properties are understood. Its structure allows for endless exploration and innovation, ensuring that the story of the elements is far from over. The periodic table's influence extends far beyond chemistry. It's the foundation for advances in physics, biology, engineering, and technology. Understanding the elements and their interactions has led to breakthroughs in medicine, energy, and computing. The periodic table is a universal language for scientists around the world. Its symbols and structure allow for clear communication and collaboration, driving progress in every field of science. No matter where you are, the table speaks the same truth. As we reach the end of our journey, remember that the periodic table is more than a chart. It's the key to decoding the universe. By understanding its patterns and principles, we unlock the secrets of matter, energy, and life itself. The table's predictive power and elegant design continue to inspire curiosity and discovery, reminding us that even the most complex realities can be understood through simple, universal rules.